Okay, welcome to Lecture 3 of Submodular Functions, Optimization, and Applications to Machine Learning. And today is August 7th, 2014. Let's just get right to it and continue on our quest to understand submodular functions. You all should have at this point read Fujishige's book. See, so now that a prominent Nobel Prize winning faculty just walked into the room, and so now I'm actually going to get very nervous. So no, I won't be nervous, given that millions of people are already watching this on YouTube. So we're in this room. I guess this is all known. And then also just a reminder to everybody that I have office hours on Wednesday from 5 to 6. And today what we're going to do is, we should actually have a label right there, but what we're going to be doing is continuing to look at various different aspects of submodular functions. We'll touch a little bit on applications again, but primarily what we're going to be starting to do is surveying some different submodular functions and starting to prove some of the properties of submodularity and see how submodularity can be defined in a number of different but equivalent ways, which is interesting in its own right. And we'll also, in looking at these proofs, begin to see constructs that are very useful that start showing up in these proofs, but in fact are still used for many of the proofs that we'll be visiting later on in the course. For example, like properties of telescoping summation and those sorts of things. So, to remind everybody what the definition of a submodular function is, I mean, we have two different definitions that we've seen so far. The first is this one, which we are, for the purposes of this class, calling submodular concave, although we don't yet know why we're calling it submodular concave. We will see that. And then the second one is the notion of diminishing returns, which perhaps, as I've said, is more intuitive to some of you. And we saw last time, we actually had a very nice sort of geometric pictorial view of this definition, and hopefully that will now give you a sort of intuitive sense of the submodular concave definition, at least as strong as you have sort of a sense of what the diminishing returns property is all about. So we started looking at these different properties. There are some functions that are submodular, but there were some functions that we didn't actually prove were submodular. So we'll see that today. Like, for example, like the facility location functions and things like that. And we're also going to start looking at various different operations that preserve submodularity, very much similar to how there are properties, or there are operations, composition and combination operations on convex functions which preserve convexity. We'll see those kinds of things for submodularity as well. Now, some of the examples that we saw last time were things like coverage functions, which could either be things like the set cover function, or just geometric coverage in three-dimensional space or n-dimensional space. Entropy functions, like the entropy function itself, and various forms of mutual information were submodular, we saw. Many different functions based on a graph can be defined, and which are in fact submodular, like the cut function and the neighbor function and the outer edge function, the inner edge function, and a number of other things. One instance we saw was supermodular, like, for example, the number of connected components function, supermodular. But we also saw one, graph strength. Remember the graph strength one? That was a really interesting one. That wasn't submodular, but I claimed that submodularity could be actually useful to solve a non-submodular problem. So that gives you a clue as to when it's the case that even if your problem isn't submodular, you can actually utilize submodular to get a solution. Sometimes an exact one, like in that particular case, and also sometimes in polynomial time, also like that particular case, which is very, very nice. We saw the matrix rank function. We saw that, we went over that in pretty great detail. And we saw a very nice geometric, hopefully what I think is very nice geometric interpretation of this particular inequality, which we will see again in 1 second. And we saw supply side and demand side economies of scale. The demand side economies of scale were called network externalities, and we justified why that should be submodular, right? That should satisfy the properties of submodular. And then lastly, we saw a model of social network influence and summarization. So here's the geometric picture again that we saw, and it's unfortunately truncating it a little bit. Maybe what I'll try to do is during break I'll fix this, but I think right now we're sort of committed to the screen. I'm having a little bit of resolution problems with this projector that we've got. But in any event, we saw that the key idea was this one on the right, that this magenta area here is going to be no greater than this blue area here. And because of that, whenever you have a function for which that's true, you have a submodular property. Namely, and then we had a term for that. We said basically that the common index, namely the information or the value or the cost or whatever it is that's being presented by the submodular function, the common index, the value of the common index, which is the magenta stuff, is no greater than the common span, which is the blue stuff. Okay, so let's start looking a little bit more at some other submodular functions. Let's define a particular type of polymetroidal rank function. And there's a particular reason why it's called this, which we will see once we define precisely what a polymetroid is. But let's just define it for right now. And let's say that, for example, S is a set. And what it is, it's a set of subspaces of some linear space. So what does that mean? It means that each element of the set is itself a subspace. It's not necessarily a one-dimensional subspace. It could itself be some dimensional subspace. And it's not necessarily the case that each element corresponds, the different subspaces are the same dimension. So they could be variable dimension. Only thing is that their dimension greater than or equal to 1. In fact, that's actually not even true. They could be, some of them could be dimension 0. But then let's say that f, the function f evaluated on a subset, basically returns the dimensionality of the linear subspace spanned by the collective set of subspaces that lie within X. Okay. So what this means and how we can think of this in some sense is that each element S, or I should say each lowercase element S, corresponds to a set of columns of some matrix. Like, for example, before when we saw in the matrix rank function, each element of the set corresponded to one column, but now we're allowing each element to correspond to multiple columns. Okay. And so in some sense, the elements of the underlying ground set, which is in this case S, are grouped together column vectors of the matrix in the matrix rank example. And so then the valuation of the function then is obtained by taking the rank function, that same rank function that we saw, and then basically for every element in the set of, the query set X, we're essentially unioning together. We're unioning together these things, and then taking the rank of the union. So we're taking the rank of the union. So it could be the case that there are some column vectors that occur more than once, but since it's a set, they don't occur more than once. But it could also be the case that the dimensions are commonly spanned. And so therefore, you're going to get that. And it turns out that that's a submodular function. It's in fact known as a polymetroid rank function. Okay. Now we're going to see that this is an amazingly interesting class of functions. I mean, right now what we're going to see is that equation 3.1 is always going to be integral valued. But in some sense, almost all of the interesting structures of polymetroid functions, which are not really that special a case of an instance of a submodular function, can be represented by something like 3.1, basically grouped matroid rank functions. Already we've got an extraordinarily powerful class of functions. Now you don't know what a matroid is yet, so you might say, well, why do I care? I don't know what a matroid is. We will spend at least a lecture and a half, possibly 2 or longer, on matroids. But matroids are inextricably connected to the matrix rank function, which we saw before. Okay, so another example which might be near and dear to you graph theorists here. Raise your hand if you're a graph person. What would we call a graph person? If you have graphophilia, for example. So raise your hand if you have graphophilia. Okay, raise your hand if you have graphophobia. Raise your hand if you do not know what those terms mean. I just made them up. But if you like graphs, then, for example, we can define a submodular function based on spanning trees. Now, what we do is we define a graph for you graphophiliacs out there. We define a graph, and you all know what those are. And you define this function R. So R is a subset of edges. Okay, so we're defining a function on subsets of edges. And what the function valuation corresponds to is, in some sense, in all senses, is basically the size of the spanning tree contained within the set of edges that are given in the argument to the function. So another way of saying that is, for example, it's the maximum size spanning forest, maximum size, so you can't get any bigger while staying a tree or a forest. It's the maximum size spanning forest in the vertex-induced graph induced by the vertices that are incident to the edges in S. Remember, S is a set of edges. So let's do a couple of examples if that's not clear. So here's a graph over here on the left. I would, if I zoom in, it's cutting it off. Well, there it is on the left. And it consists of 8 nodes and 12 edges. And I'm choosing a subset of the edges, which is edges 1, 2, 3, 4, 5, 8, 9. And then taking the induced graph from the vertices that are incident to the edges that I've chosen, which basically gives us this graph. But then there are 2 spanning trees. Well, there's actually more than 2 spanning trees, but you notice that the size of these 2 spanning trees within that span this graph, spanning basically means all vertices are there. It's the same size, namely that the value is going to be size 5, right? So the value of R of S is going to be 5. That turns out to be a submodular function. And it turns out that that's also equivalent, as we'll soon see, to a matrix rank function, and also equivalent to a matroid rank function. So we just are going to visit the supply side economies of scale again. I mean, here the idea was that if you are, say, a company and you are producing goods, and you already have essentially a collection of goods that you're producing, chances are that if you're interested in producing a new good, that the cost of that new good is going to be, the cost of adding that new good to your production line is going to be less if you're in the context of producing already a larger set of goods than if you're in the context of producing a smaller set of goods. And the example we gave was paint. Using paint, where if you're producing green in the context of blue and yellow, it's easier than if you're producing green in the context just of blue. And that was, we now see that that's clearly a good instance of submodular. Submodularity is a good model for that. And we also saw instances of social network models where the influence, everybody potentially could be influenced. You have some influence function, which every node in a network has an influence function, f of v, and it maps from subsets of other nodes. And it's really only thing that matters now is the neighbor node. So like f of v of a is basically equal to the value of a intersected with the neighbor function, which we now know. So basically, if anything other than your neighbors are influenced, then you're not likely to be influenced. But as more and more of your neighbors are influenced, the propensity of you to be influenced increases. So it's not really a concave function, but let's say that f of v is some submodular function, right? So that basically would mean, and that seems sensible, that basically the degree that, say, Jim over here, how influential Jim will be depends on how many other of your friends are already influenced. And if you're already, say, over the threshold that, yes, I will buy that product, Jim's influence doesn't matter at all. Okay, so there are a lot of different ways in which, for example, you can express this idea, all of which can be well represented by a submodular function. And then if you're interested in identifying individuals who will lead to the greatest influence throughout the entire network, where influence is essentially determined by a random process where basically you have the influence function and you're influenced based on some random variable, and if the threshold is above the outcome of the random variable, you get influenced, that whole process ends up being submodular. So that again seems like a very, very natural model for influence in social networks, or viral marketing, or viral outbreaks. The value of a friend was another example we saw. I mean, I don't need to talk about this again, but again, I think you can see that it seems maybe reasonable. I mean, in a sort of from a cynical perspective, maybe submodularity is a good model for the value of a friend. However, if you're a truly moral person, then your friendship models are supermodular, right? That should make sense. Raise your hand if that makes sense. Raise your hand if you think you are a submodular person or a supermodular person. I won't hold it against you, you submodularists out there. I won't. I'll do it. I'll turn my back. Okay, you decide who you are. All right. So then, since summarization is another example for which it seems reasonable to utilize a submodular function for, namely, if you've got a piece of information and you're interested in how useful that information is, well, the more information you've already got, the more chance that information is redundant with what you already have. And so therefore, submodularity is a very, very good model for summarization problems. Now, we're going to get a lot. We're going to discuss quite a bit about submodular polyhedra and submodular polytopes. I just want to sort of introduce them to you. What's interesting about them is, which I'll talk about right now, is that you can actually define, first of all, let's define submodular polytope. So this is it's all vectors in R to the E, right? So it's an E-dimensional space that satisfy this inequality for all subsets S less than or equal to E. So basically, that basically means that there's an exponential number of constraints in the submodular polytope, right? And we can also define the non-negative orthant version of that polytope, and also one that, for example, intersects a particularly interesting and useful hyperplane, namely the hyperplane x of e is equal to f of e. Now, consider this particular linear programming problem. So you want to maximize, so c is a constant, you want to maximize over x in that polytope the dot product between c and x. So ordinarily, linear programming with an exponential number of constraints is hard. But if it's the case that the polytope, so if this polytope, P of f, is defined with f being a submodular function, then it turns out that the greedy algorithm can actually solve it in very exactly in low order polynomial time. Now, that when you first see it may not make sense, but what we will do in the coming few weeks is we'll understand this both mathematically and intuitively and graphically, and you'll basically see this and you'll say, oh yeah, I see how it makes sense, geometrically even. But then if the function's not submodular, then that guarantee doesn't exist. You can't get that polynomial time solvability. This was a property that was discovered by Jack Edmonds in the late 1960s, or in the early 1960s, depending on who you ask. Just a little bit more on notation. So people generally tend to use E or V as the ground set, namely the set for which you're taking subsets of to evaluate a submodular function. E is often used like when it's a set of edges of a graph, and V when it's a set of nodes, and when it's neither, you might use E or V. So we're going to sort of continue the tradition of inconsistency and inconsistently use both. So we'll use both E or V. So hopefully, not in the same equation, you will see E or V as the ground set. But we will generally tend to avoid and hopefully not at all use E or V as subsets of some ground set. Something else about this notation, sometimes people are a little bit confused about what this means. So a vector in R to the E, this basically means that E is a set, E is a ground set. And what this means is that you're in an m-dimensional space where m is the size of E. Oops, let me just draw this with a pen. M is equal to the size of E. Okay, except that the dimensions are indexed by the elements of E. So that basically means that this set, R to the E, is basically all x, where the jth element for all j in E is some real number. Okay, and then the RE plus is basically just the positive orthant, that intersected with the positive orthant. And so then any vector, we can say, okay, well, here's the vector. We can essentially treat that as a modular function. So we'll do that a lot. We'll say x in R to the E is a normalized modular function. No, it's modular because basically when we say x of A, all we're doing is we're summing up the corresponding coordinates in the set A, corresponding to the elements in the set A. And it's normalized because basically we're just defining it. If it's a vector, then x of the empty set is equal to 0. So vectors can be seen as modular functions. And we saw last time, the characteristic vectors is a particularly useful one. If we've got a set X, we're defining the characteristic vector 1 of A in RE plus as basically 1 if the element J happens to be in A and 0 otherwise. So it's just called the characteristic vector. So you should know that, and we will be using that. Sometimes people use chi. We're going to use 1. Another way of writing this is that x of A is equal to x dot product times the indicator of A, the characteristic vector of A, which is also equal to just summing up all I and A of the element-wise sum. So hopefully this will remove any uncertainty you have about this particular notation. But I also thought that, one other thing about this notation. So officially, if we want to be exact, when we want to add a singleton element, we would turn it into a set, like A union the set K. But we are just going to say that this is the same as that. So we're not using the braces. Just people should be aware of that. It's a little bit of a notational shortcut. So X is essentially just this ground set. Well, well, either V or E is the ground set. Where X here, do you mean? No, X is in this particular, so X is a vector in R of E. So X is not the ground set, right? X is any vector. So if E consists of two elements, then X is a two-dimensional vector. And then we can use the elements of the set to index the first axis and the second axis. So let me give, if that's not clear, let me make an example. So maybe we have E1 and E2, and maybe this would be X here. Right, so it's got a coordinate in the E1 dimension and a coordinate in the E2 dimension. Right, and this would be X of E1, and this would be X. This would be X of E2. Okay? And so, but in n dimensions, it's just some point in n-dimensional space, or E dimension. We say E-dimensional space even though E is a set. It's not a number. But it's well defined nonetheless. Everybody got it? Yes? Okay. One last thing I thought would be fun to talk about is that what does this notation mean? S to the t, where S and t are both sets. It turns out that this is a fairly standard notation that you've probably seen before without knowing it. But basically, let's say that S and t are two arbitrary sets. They may be countable, they may not be countable. What it really means is that when you write S to the t, that basically corresponds to all functions that map from elements in t to elements in S. So that means if we say that f is a member of S to the t, then that means that f is a function that maps from elements in t to elements in S. So here's an example of that notation in action. We've got a finite ground set E, R to the E. It's basically a function that maps from elements in the set E to real numbers, right? It's a vector in E-dimensional space. Basically, you can think of it as a vector as a function that maps elements to real numbers, right? Its coordinates. That's what basically this is down here. Or equivalently, if we take 2 to the E, why do we use that? That's a further shortcut. Basically, it's really, the number 2 is really this set, 0, 1. So when you write 2 to the E, it's really 0, 1 to the V. And then what that is basically all functions that map from elements in V to either 0 or 1. And so that basically, it's a binary vector. It's a bit vector corresponding to the set V. And if an element is in V, then basically it's a 1. If an element is not in a set, then it's an if you have a subset of S, subset of V, let's say that S is a subset of V, then a bit vector version of S would be basically a member of 2 to the V. Okay. So, like, for example, a submodular function, when we say a submodular function, it maps from 2 to the V to R. That basically means that it's a function that maps from functions from V to the binary number to the real numbers. This is hopefully making things clear and not making things obscure. What do you think, for example, just as a sanity check, what do you think 3 to the E might mean? So if 2 to the E means this, 0, 1 to the V, what might 3 to the E mean? Right, it maps to 0, 1, 2. So basically it's all functions that map from elements in this set to either a 0 or a 1 or a 2. And that actually is a useful notation that people use to define various extensions of submodular functions, which we will eventually talk about in this class. Okay, so let's just go through some simple properties. Are there any questions so far about notation? That's the end of notation for now. It's a little bit boring, but we have to get through it. Okay, so you can take two submodular functions, f1 and f2, and you can sum them, and you preserve submodularity. So submodularity is closed under summation. And it follows immediately by just writing down the definition, because when you have f1a and f1b is greater than or equal to f1 of a union b and f1a intersect b, and same with f2a and f2b is greater than or equal to f2 of a union b plus f2 of a intersect b. Okay. And then that basically just by summation corresponds to f of a union b plus f of a intersect b. So therefore, summing preserves submodularity. And in fact, we can take any non-negative combination of submodular functions, or any non-negative conic combination of submodular functions is submodular. So submodularity is closed under non-negative conic combinations. Okay. Summing a submodular function and a modular function. Do you think that's going to preserve, or could that hurt submodularity? Sorry, suppose the modular function is negative. Could that hurt submodularity? Probably not, right? Because basically the modular function is one for which the inequality is always inequality. Right? So let's say that we define this function f of a, which is equal to f1 of a minus m of a. It could be plus m of a, but I'm writing minus m of a to sort of emphasize that the sign of m doesn't really matter. And this is submodular, and the reason why, again, is because this part of the function, m of a minus m of a minus m of b, is equal to minus m of a union b minus m of a intersect b. So the stuff in the intersection is counted twice on both sides of the equality, and then the rest of it follows from submodularity. Namely, this, this, and this, and this. So the modular component never destroys the inequality. And of course, the other thing to realize again is that if m is modular, then so is negative m. So we can flip m, and it stays. There's not. You can multiply m by any constant, positive or negative, and you've preserved modularity. This one is an important one. This is a restricting submodular function. It basically says that, let's say you've got some submodular function defined on 2 to the e, and now you have any arbitrary subset S, and now you define a new submodular function who's defined on the same domain, but whose valuations are restricted to only those values that intersect the argument and namely a and the set S. So namely f prime of a is equal to f of a intersect S. So that also preserves submodularity. And so to prove it, we can do it by considering the diminishing returns definition of submodularity. So basically, in order for this to be submodular, then equation 3.20 must always be true. Right? And there's two cases to consider. In the first case, V is not a member of S. So if V is not a member of S, then when you intersect with S, everything gets canceled out, and the differences on both sides are zero, right? Namely, because adding V to A intersect S is the same as not adding V to A intersect S, because S kills off V, and same with B. On the other hand, does everybody see that? On the other hand, if it's the case that V is a member of S, then we can consider this problem, where we write the valuation as A prime plus V minus f of A prime, where A prime is equal to A intersect S. So we essentially take the stuff in A in S, and since adding V to A, since intersecting by S doesn't do anything to V, it basically leaves it there, we can just add it after we've done the intersection through set theoretic arguments. And the same with B. And it's even the case that if, say, V is not in A, but it is in B, this basically works, right? So then this holds, again, because of the submodularity of F. Okay? So it's just sort of changing the problem back to one that we already know. So therefore, what we can do is we can actually sum restricted submodular functions. So we can define a submodular function on V, on 2 to the V, and we can define one, let's say that F1 and F2 are both submodular functions defined on 2 to the V, and we can construct a new one thusly. So it easily follows from the two preceding results. Now you might think, why is this important? Well, this is particularly important in computer vision applications, because when it turned out that when people discovered, there was a paper in 2004 where people discovered that many of the procedures that people use for solving Markov random fields exactly using graph cuts, and that those corresponded to submodular functions. The particular type of submodular function that those corresponded to something akin to equation 2.3. At least the energy function did correspond to this. And the way this works is that you take, maybe there's some sort of potential, but you have a set of cliques, say, in some graph. Let's say script C is a set of cliques which consists of the cliques C1 through CK, right? Each one of which is a subset of the nodes. And if it's just a regular Markov random field with, say, a grid structure, then each clique is of size 2, right? And then what you're doing is you're saying, okay, I'm defining a function, f of a. These are like, in some sense, the pixels that are turned on, or the pixels that are labeled 1, I should say. You're defining an energy function which basically sums over all edges of the energy that's been restricted to that particular edge. Okay. And so basically what the valuation determines whether or not A contains both sides of the edge, namely both vertices, in which case it's not part of the cut, or it contains neither of the vertices, which in case it's also not part of the cut, or in which case A and C intersect in only one element, in which case it in fact actually gets you a cut. That becomes an edge that's part of the cut. And so that's a submodular function right away. So image processing, graphical models. We'll revisit that again. Another example that we saw before, and in fact, when we defined the facility location function, you were asking why is the max function a submodular function? So here we're going to prove it. And the proof is actually very nice. By the way, a lot of these proofs that we're doing, these are, there are actually a lot of different ways of proving them. The ones that we're doing are most of the time the simplest instances of the proofs. But there's there are a couple of examples where that's not the case. Probably because I'm going to ask you for your problem set to find the simplest version of the proof. But here's a function. Basically, we have a vector, C, which is a non-negative vector. It's a fixed vector. And we're defining a function by taking the max of whose value comes from taking the max of the elements just within the argument, namely A. Okay. So that's part of the facility location function, if you remember. Now this function is submodular. Now why is it the case? Well, here we're going to use this sort of submodular concave definition. That's the easiest way to prove this. So what we want to do is we want to consider this inequality, and we want to argue why this thing is true. Okay, so the first thing first follows from basically taking if we take the max of this and this, that's going to be equal to this, right? Because when we take the max of a set of elements in A and the max of a set of elements in B, we can't get more than the max of one of the elements in the union. So therefore, we've got this inequality. And let's, without loss of generality, assume that this guy is equal to this, the left one. Okay? And then if we take the min of these guys, which is the remainder, that one's going to be greater than this one. And why is that? Because A intersect B is always a subset of A. Max is in some sense a monotonic function of size of the subset. And so basically, if we take a max over only A intersect B, that's always going to be no greater than the max over either A or B. So therefore, combining these two things together, we've got the submodularity of the max. So now what we said was that C has to be a non-negative vector, and we're also taking f of the empty set to be 0 so that it's a normalized max function. We don't actually even need that. We can say that C is any real valued vector. So C is think of C itself as a modular function, or C as a vector in R to V. Then this function here is submodular where it's not necessarily normalized. Basically, we can take f of the empty set to be any value less than or equal to the smallest value of the vector. And the same proof basically holds. So you could, for example, case statement it or something. You could say f of A is equal to this if f is not the empty set, or if if A is the empty set, then choose some value which has to be less than the minimum. Then you've got submodularity. So here's the uncapacitated facility location function that we saw before. And so now we immediately see, I'm not going to go through the details of this example again, but we immediately see that this is a sum of two things. First of all, it's a modular function on the left. Secondly, it's a sum of max functions. So for each term in the sum, we've got the sum over I in f, and we're summing up all over all these max functions. So we're on the right-hand side, we're summing a bunch of submodular functions. On the left-hand side, we've got a modular function. Therefore, we've preserved submodularity. Hence, facility location is submodular. Everybody with me? Okay, stop me if there are any questions. Remember, the only bad question is the unasked question. Famous adages spoken by bad professors. Right? Okay, so what do we have here? So, all right, actually, we just said this. So, the facility location is submodular. All right. Any questions? So we anticipated this slide. Okay, so here's one that might be of interest to some of you. The log determinant function. So let's start off with sigma, which is n by n positive definite matrix. And let's say that V, the ground set, is basically a set that indexes the elements. It's a square matrix, so it indexes the elements of the rows or columns. Right? And let's define submatrices by subsets of V. So that basically means sigma sub A, which is namely this thing here, is a square matrix which is obtained from sigma by taking the corresponding rows and columns. So, I mean, if you want to picture basically, like here's a square matrix, and maybe we'll take, if this might be 2 and 5, and this might be 2 and 5. So we take a 2 by 2 matrix consisting of this element, this element, this element, and this element. Okay, so it's still square. And that's what sigma A is. Okay? So we can define a function, a set function, based on the log of the determinant of the submatrix sigma sub A. Okay? So it's each time we choose a different A, we're taking a different determinant, right? It's not like it's a completely different matrix. It's a different dimensionality matrix. Is it still positive definite? Raise your hand if you think yes. Raise your hand if you think no. So it's not? Why?
Lost them in negative, right?
No, is the matrix still positive definite? Yes. The answer is yes. The sigma is a positive definite matrix, and we're taking a submatrix corresponding to the rows and the columns. Yeah, I'm not talking about log being negative. Okay, so now the question is this a submodular function? Now, there's actually a really long and not so easy way of proving this, but there's actually a really easy way of proving this. In this case, we're going to use the really easy way. The reason why this has actually become very of great interest in the machine learning community, because the log determinant is something that's critical for determinantal point processes, which has recently become very important. And the log determinant function, the function that gives you essentially something that's very important associated with the determinantal point process, and basically, namely, it gives you a strategy for finding the maximum value or finding the approximate maximum value. It turns out to be submodular. Now the question is, why is that? It comes from essentially the submodularity of the entropy function. In this particular case, however, it's the Gaussian entropy function. So it's interesting to note that we don't know this yet, but I'll tell you now that the Gaussian entropy function is the entropy of a multivariate Gaussian in a continuous space. But there's a larger class of submodular functions, which is the entropy of the non-Gaussian continuous function. And then there's a larger class of functions still, which is the polymetroid functions, which is strictly greater than the entropy functions. So submodularity is in some sense much richer and more than just the log det function. Okay. But let's first of all come up with an easy proof, again using the submodularity of the entropy, why log det is submodular. first of all, here's the Gaussian entropy, the differential entropy function. It's basically the log of the square root of the determinant of 2 pi e sigma, right? It's one of these cases where you have pi and e in the same expression. And you can write it as, in this fashion. And so therefore for a particular subset, you just basically take log of the square root of 2 pi e to the a and then the determinant of the submatrix. But right away, you can see, thanks to the properties of the log, that that's equal to a modular function, which comes from this stuff here, plus 1/2, which is the square root part, times the log of the determinant. And so now we have a function. The log det function is a modular function plus a non-negative constant times the log det function. So we subtract off the modular function, multiply by 2, and we've got log det. And we know that subtracting modular functions and multiplying by non-negative constants preserves submodularity, and so therefore log det is a submodular function. Okay? And you don't even need positive definiteness. Semi-definiteness is sufficient. Leave that as an exercise. Okay, so let's summarize so far, and hopefully this will be an opportunity for you, if there are any questions, to ask questions, or if it's obvious, then don't ask questions. So
proof is that the entropy is submodular and that's right.
Yes, the entropy, it comes from the submodularity of the entropy, and we can prove that by looking at that comes from the non-negativity of the conditional mutual formation for the differential entropy case, which comes again from Jensen's inequality. So remember, mutual information is always non-negative. Conditional mutual information is always non-negative. Conditional mutual information is equal to the sum of two entropies minus the two other entropies. That's always non-negative, therefore submodular. Okay, so what do we've got? Non-negative conic combinations preserve submodularity. Restrictions preserve submodularity. The max function is submodular. The log det is submodular. Okay. Questions? Okay, so here's an important one. Let's say that m is a non-negative modular function. Okay, and g is any concave function over R. Okay, so what we're doing is we're composing the output of the modular function on set A with the concave function and defining a function this way. Then it turns out that f is submodular. So in other words, we call this sometimes concave over modular. Concave over modular is submodular. Now why is this the case? Well, let's use the diminishing returns property. So first of all, let's define A, which is A is a subset of B, which is a subset of E except for V. So this notation, by the way, we use a lot. So I can't zoom in there, but let's just think about this for a second, okay? So what this means is that A is a subset of B, obviously, but E is our ground set. E is fixed, and we're saying B is a subset of E except for V. So we're by saying that, we're singling out an individual element V, and we're saying that V is not contained in B. Right? So B can't be the ground set. B cannot contain V, and that's what that notation means. It's just a shorthand for that. Okay, so we've got A and B and V. And let's define lowercase a, which is m of a, and it's going to be non-negative because we're assuming that the modular function is non-negative. And that's going to be less than or equal to b. And why is that? Because we're summing up more non-negative elements, m, right? Because b is a superset of a. So it has to be, can't be any less. And let's say that c is also non-negative. It's just the valuation of m at v. Okay. Now, this is a property of concave functions that you may or may not know. So let's just draw a picture. I mean, but it's not too difficult to prove. But if we've got basically let's say that here's A plus C, and here's B, and here's B plus C, you've got some concave function, then what it's saying is that this delta, or this increment, is going to be greater than or equal to this increment. So in other words, this green distance, or this green height, is going to be greater than or equal to, say, this little magenta height there. And so that's what we're using right here. Okay? So that follows immediately from concavity. And so using that property, the property of, and that in some sense is the diminishing returns property. I mean, concave functions have a diminishing returns. The more you go, if it's a concave one-dimensional function, the more you go to the right, the less any fixed increment is going to buy you in terms of valuation. In fact, it could even start going down. Right? If it doesn't have to be monotone, it could start going down if you keep going to the right, if it's a concave function. So therefore, when we then look at, we just plug in this stuff. So that's g of a plus c minus g of a is greater than or equal to g of b plus c minus g of b. So therefore, submodularity holds. Now, is the converse true? Let me just ask you this as a sanity question. So I'm saying a form of converse. So what do we mean by that? So what the converse would say is that if we've got this particular thing, and it turns out to be submodular, does that require G to be concave? Turns out that it doesn't. Think about what the concave function needs to do. It only needs to be, in some sense, concave on those points that it gets evaluated on via subsets of A and the corresponding value summing up M out on the subsets of A. So in other words, the function G could be do all sorts of crazy stuff in between these possible valuations and not concave at all. It just needs to be, in some sense, it needs to have a diminishing returns property. So it needs to have this property on the possible set of valuations, but it doesn't need to be concave at all. On the other hand, we have a stronger converse, in some sense, that says basically that these two conditions are equivalent. So that if it's the case that for all modular functions, key on for all, if for all modular functions, M, then F defined in this particular way is submodular, then that's basically equivalent to saying that G is concave. Because basically now you're saying, okay, well I can put those valuations anywhere. And on an uncountable set of modular functions. Okay, so there's the notion of a polymatroidal function. So we're going to sort of define what a polymatroid function is without knowing why it's called a polymatroidal function. But basically, if G is a non-decreasing concave function whose valuation at 0 is 0, then basically that function G, namely a concave over a modular, is going to be an instance of a polymatroid function. I should add that G of 0 has to be equal to 0.
When you say G is non-decreasing concave, you just mean here?
No, I mean it's non-decreasing concave. So this is the instance of do we say more than or not less than? So we're trying to be precise about, rather than saying it's an increasing concave, we're saying it's a non-decreasing concave. So this would be an increasing concave function. This would be a non-decreasing concave function. This would be a non-decreasing concave function, but it's not an increasing concave function because it saturates. It sort of truncates and stops increasing, but it's still not decreasing, so it's a non-decreasing. So the requirement, basically saying that it's as general as it needs to be, the general way of saying that would be to say it's a non-decreasing concave function. So if we were not being as pedantic, then we would say increasing. And in fact, a lot of people say increasing, in short. Like when you're having conversations back, like when Rishabh and I are talking, we're always saying increasing, and then when we write it, we often forget that this is really non-decreasing. I'm usually one who's the pedantic one. Although Richard always knows what I'm talking about, or what he's talking about too. So anyway, so let me. All right. So where are we? So okay. So then sums of concave over modular functions are modular. Now this, it turns out, as we will see when we start looking at some applications again, this is a critically important class of submodular functions for machine learning applications. One of which is that they're very general. But on the other hand, they're also quite scalable. And they're general in the sense that you can actually, with them, represent graph cuts and bipartite neighborhoods and set covers and all sorts of things. And feature-based functions, they're really nice class. On the other hand, you can't do a simple cycle matroid rank function with them, amazingly enough. So somehow the matroid rank function is a richer, even on a simple little graphic matroid. And graphic matroids aren't even all matroids. There are matroids that are non-graphic that have rank functions. But a simple little graphic matroid function can't be expressed in this way. So it's an amazing result. Okay, so are there any questions? I guess this is a good. Is this a good time to take a break? Yeah, this is a good time to take a break because it's between sections. So if there are no questions, I'm going to try to see if I can fix the screen resolution problem during the break. But one of the things I like to do, before we take a break, oftentimes people will come up to me during the break and they'll ask me a really good question, and I'll say, would you mind asking me that question during class so that everybody in the class can benefit from that? The reason why I like to do this is because I want everybody to hear the question and benefit from the answer to the question. Okay, so if you ask me a question during break and I don't answer it, then don't be offended. Okay, and don't be nervous. Don't be nervous about asking questions in class. Remember, the only bad question is the question unasked. So okay, I'll see you after break. Okay, everybody, welcome back to part 2 of the lecture. Let's just continue forward and just do a couple more definitions. So the notion of monotonicity is very important. The word is monotonicity, not monotonous, which is something that I've heard people use before, but it's actually monotonicity. So a function is said to be monotone non-decreasing if it's the case that basically whenever you take a superset, the value doesn't decrease. So if A is a subset of B, then the value of A is no greater than the value of B. And it's called strictly monotone increasing, which is sort of a strict form if it's the case that supersets always strictly increase the value. And another one of these, this is a monotone non-increasing function. So there's a monotone non-decreasing and monotone non-increasing, which really means sort of a non-strict version of monotone decreasing, which is the opposite. Basically, if it's the case that you've got a superset that the value either can't increase or the value strictly decreases. Okay. Yep.
Is there any bearing on the size of A and B itself? So for example, if A and B were disjoint, but size of B was greater than size of A, and that was a monotonicity.
No. So in this particular, the definition of monotonicity only involves sets for which B is a superset of A. It could be the case that disjoint subsets, there could be any valuation. You could have a larger set that has a smaller valuation. Take, for example, the matrix rank function. I could have 100 vectors, all of which are scalable multiples of some underlying vector. And so the size is 100, but its rank is 1. On the other hand, I could have 5 linearly independent vectors, and its rank is going to be 5. So the multiplicity of the set, the size of the sets, aren't what we're talking about here. It's strictly, although there are. I'm going to be very careful. There's a matroid axiom, which when I define involves sizes, and I'll be careful to point that out. But in this particular case, I'm not talking about that. Okay, here's a very important lemma, maybe, or theorem, I don't know. So you've got two functions. One is a set function, f, and another is a continuous value, 1. So g maps from R to R. And what we're doing is we're forming a new function h, which is the decomposition of g and f. So it's basically h is g applied to f of s. So then that composition, h, turns out to be non-decreasing submodular if it's the case that g is itself non-decreasing concave, so namely g looks like this, and f is non-decreasing submodular. So what that means is that we can take any non-decreasing submodular function we want and slap a non-decreasing concave function on the outside of it, and we've got a submodular function. So, like, for example, this mimics what we've already seen, because if we take a non-negative modular function, right, a non-negative modular function is a non-decreasing submodular function, right, because all modular functions are submodular, but if it's a non-negative modular function, every time we add an element, we're certainly not decreasing the value and potentially increasing the value. And then if we apply a non-decreasing concave function onto that, we're going to turn it into a submodular function. But here, in some sense, it's a little bit stronger because we're saying it's stronger and weaker at the same time, because we can take a polymetric function or non-decreasing submodular function and apply a non-decreasing concave function on that and still retain submodularity. So it's related to that. It's not really stronger or weaker. Now, what about mins? So is concavity preserved by taking the min? So we saw that, for example, submodularity sort of shares. I mean, we're going to see this in a lot of ways. That, you know, here we're taking concave functions and composing them with submodular functions, or taking concave functions and composing them with a modular function, and we're getting a submodular function. And there's this notion of diminishing returns in concavity already. So, and there's a notion of diminishing returns in submodularity. So therefore, it seems like submodularity and concavity should go hand in hand, right? Now, is that always the case that they go hand in hand? No, as we will see. Now, here's one instance where they maybe go pinky and thumb or something, as opposed to hand in hand. And you might think, oh, well, since it's the case that concave functions are closed under taking mins of two of them, you know, like if you've got one concave function, another concave function, and you take the min, you've got this stuff in the middle, which is still concave. Maybe that's true also of submodular functions. But unfortunately, that's not true in general. But it is true if the two functions have a relationship with respect to each other, namely that their difference, f minus g, so we've got two submodular functions, and we're saying that their difference, f minus g, is either monotonically increasing or monotonically decreasing. So that basically means that as we add more items to the set, those values have to either strictly non-increase or strictly non-decrease. Whatever that means. Strictly, no, it means that either you have to non-increase or non-decrease. Okay. So let's prove that. So we're defining h to be the min, right? And now we're going to consider two cases. Let's suppose that h agrees with either f or g on both x and y. Okay, so that basically means that let's say it agrees with f. Okay, so that means that h of a is equal to f of a, and h of x is equal to f of x, and h of y is equal to f of y. That would be agreeing with f on x and y. Now we have the submodularity of both f and g. Right? This is something we definitely have, right? So therefore, the submodularity in this particular case follows because, you know, when we look at this min, this is the min of f and g on the union plus the min of f and g on the intersection. So since, let's write it this way. So since it's the case that f of x plus f of y is greater than or equal to f of x plus f of y, f of the union plus f of the intersection, it's going to be greater than or equal to the min of these guys, because that can only be smaller. And similarly, these guys, which can also be smaller as well. And since the min doesn't disturb the left-hand side, either it agrees with either this guy or this guy. In one of those cases, this is going to be true. And so therefore, submodularity holds in that case. Okay. Now, suppose on the other hand that it doesn't agree always with either f or g on both x and y. And so without loss of generality, let's say, okay, well, h agrees with f on x, and it agrees with g on y. So how do we prove submodularity in this case? So let's start with this. So h of x plus h of y. So let's just plug in the values that they agree with, which is f of x plus g of y. So now let's use the submodularity of f. Okay, so f of x is greater than or equal to f of the union plus f of the intersection minus f of y. Right? How's that submodularity? Raise your hand if you see why it's submodularity. Right, because all we're doing is we're just moving this guy from one side to the other. Okay, so we've got that now working, which follows from submodularity. But now we're going to use the monotone increasing case. So f minus g is monotone increasing. So what that means then, if we move this guy over to the left and this guy over to the right, we're seeing that f of the union minus g of the union is going to be greater than or equal to f of y minus g of y. That's the monotone increasing property. And then rearranging that, we've got this valuation here. Okay. But now we can just associate f of the union with this f of the union, g of y, which is equal to this, minus f of y, which is equal to this, and therefore replace these three things with g of y, and what we end up getting is h of x plus h of y is greater than or equal to g of the union plus f of the intersection. Okay, there's one last inequality to show, which is this one. So why does this last inequality hold here? By the definition of h, right? H is the min. And so we're using submodularity to get this stuff. Then we're using the monotonicity to get this stuff. And then we're using the definition of h to get this stuff. Therefore, it's done. Oh, one last thing. So in order to prove that the opposite is the case, that it's also true when f minus g is monotone, decreasing as opposed to increasing, what do we do? You just switch them. Just switch them. Yeah, switch f and g. And then it becomes monotone increasing. And use the same proof. The names don't matter. Okay. Okay, so any questions on that? So let's now talk about the min function. So there is a form of min that actually does preserve submodularity, and this is also a very, very important one for use in applications. Because basically what you're doing is you're taking a submodular function f and you're sort of truncating it to k. So what this kind of does, and this can be useful for a number of different things. Like you can say, well, f might continue to be increasing, but I want to sort of truncate f so that I no longer get any value from f after it reaches this critical point. Like maybe f, increases in this sort of nice, smooth, concave-ish like fashion, but then eventually it truncates once it reaches value k. Right? And that can happen for a number of reasons, mainly because you don't want, let's say that f is some component in some large sum of submodular functions. You don't want any one component to dominate. Okay. Yep.
In this diagram,
Yep.
What is the x-axis?
Well, in this particular case, the x-axis would correspond to the value of a modular function that's being fed to a concave function corresponding to the min of k comma alpha, where alpha is the valuation. So it would be really alpha. So if you were to write, like, say, min of k and alpha, then this would be alpha. Right, so alpha keeps increasing. I mean, this actually, well, in that case, it would be linear. But let's say it's some concave function of alpha. So it's the square root of alpha. So it goes up as a square root, and then it saturates, truncates.
And on which axis was A diagonal? Because that is
Well, A is a set. So when we plot this is why I use the phrase concave-like, because remember, a submodular function is not a concave function, but in some sense we're drawing only the last stage of the function, which is the thing perhaps that turns it into a submodular function. But on the other hand, we're not necessarily doing that because f itself could be any non-decreasing submodular function. Okay, as we'll see. So what we're really talking about here is just, in this diagram, we're talking about maybe a specific case of like where f of a is equal to the square. Like you can imagine if f of a is equal to the square root of a, and what we're plotting here is alpha is equal to the size of a, and we're plotting the min of k and square root of alpha. So we're plotting it on the alpha axis. Okay. Does that make sense? Any other questions about that? Because you can't really plot. I mean, you can't plot a submodular function on a one-dimensional axis. I mean, when you plot a function, the horizontal axis has to be real. The submodular function is defined on subsets of a set. You can actually sometimes plot valuations of a submodular function, like in the case when you have. I'll just mention this. Like if you have a two-element ground set, you can plot it on like a hypercube, where this would be 0, 0, 1, 1, 1, 0, 0, 1. And submodularity would mean necessarily that the sum of these two, the sum of the valuations at these two vertices has to be greater than or equal to the sum of the valuations at these two vertices. So green diagonal is greater than or equal to purple diagonal. That's a nice little useful thing. We'll see a picture of that in latter. That corresponds, that's similar to the Monge matrix example that you saw in lecture 1. Okay, so why is this the case? Well, for constant k, we have that f minus k is either increasing or decreasing. So this follows immediately from the previous result. Right. Because remember, we said that this is a monotone increasing or a monotone decreasing submodular function. Another way of looking at it, this is sort of similar to what we were saying. So g of a is equal to min of k comma a, when seen as a function of a, is itself a concave function, right? What does that function look like? It looks like this. Goes up and then it truncates at value k. Right? So that's concave. It's not smooth, but it's certainly concave. So therefore, all we're really doing is applying a concave function onto a non-decreasing submodular function in that particular case. Now, this is actually useful for a number of other reasons. There's something called the min trick or the saturation trick, where, sometimes like in applications, let's say that you have two functions which measure sort of a notion of diversity, but they're sort of different notions of diversity. And you want to make sure you're diverse with respect to both of these notions of diversity. Like maybe, for example, I've got balls, I've got an urn, and, sorry, I always laugh when I think about balls and urns. I don't know why. It just seems like a strange example. But anyway, you've got an urn. Like we all, every day, we want to stick balls in urns. And in this particular case, we care about making sure that there's lots of different colored balls in the urn and also lots of different sizes. Big balls, medium-sized balls, and small ones, and as well as red, green, and blue. So we have one function which judges the number of colors in the urn, another submodular function which judges the number of sizes, number of different sizes, neither of which judge the number of balls that are in the urn. And we want to make sure that both there's a large number of colors and a large number of sizes, and so you might want to say, well, let's maximize the min of those two submodular functions to ensure that you're diverse from the perspective of both color diversity and size diversity. But that, unfortunately, is not a submodular function. But what you can do is use this min trick and saturate trick, and when you want to maximize the minimum of two submodular functions, what you can do is define a surrogate function, h, which is the sum of the two mins. So let's say that f is the function that judges color, and g is the function that judges size, and we just take the average, both of which are truncated at k. And this is it's a surrogate, it's a submodular surrogate, and it has the property that h is greater than or equal to k if and only if both f is greater than k, equal to k, and g is greater than or equal to k. So if you maximize h, and if you achieve a particular value k, you're guaranteed good with respect to these two functions. Now that maybe isn't as good as being able to maximize the true min of f and g, but on the other hand, it can actually lead you to a strategy to maximize both, and also can lead you to various bicriterion approximation strategies, which we may get into later in the course. Now, there's actually it's an interesting study of just the whole notion of submodular surrogates. Like, when is it the case that you have a non-submodular function? And this is what I mean, what I said earlier about using submodularity as a vehicle through which one can solve non-submodular problems. You have a non-submodular function, but you define a surrogate submodular function, which you can prove that when you optimize that surrogate submodular function, something good happens in the original non-submodular function. So this is the first real example of that thing. But there are other examples as well. There are other, as we will see. And it's actually an interesting area of study. I think that is still somewhat underexplored. There are a bunch of other potential examples. Oh, in fact, here's that discussion. Okay. Any questions about submodular circuits? Yeah.
So in this case, if you are maximizing two monotonicity modular functions, that means you are trying to maximize f and you're trying to maximize g, or you're trying to maximize the sum of f and g.
Well, in general, what we would like to do is maximize, let's say that I have some function, I don't know, L of A is equal to the min of f of A, comma g of A. Problem is that L of A is not submodular. That's what we would like to maximize, because we want both a large number of colors and a large number of sizes, right? That's the example. And if we maximize the min, then we're assuredly going to make sure that the urn is rich with color and size. Maybe flavor. Maybe these could be like, another one could be flavor, like if these are gumdrops or something, or what are those jawbreaker things you buy in the supermarket? So it's rich with flavor as well. Like you want the blueberry and the raspberry and the strawberry and the boysenberry. Right, blackberry, can't forget that. All right, so everybody see what's going on? You could actually have three and this actually would generalize to more than two submodular functions, to three. So we could actually have the flavor component as well, which we want to ensure it has high diversity. Same property would be true. Okay, questions about this? Okay, so here's another interesting property which we've used, and I think this is something that is potentially, very useful for many applications. For example, in things like graphical models, or for non-submodular optimization procedures. But basically, the property is the following. It says basically, let's say that you have some arbitrary set function f, which isn't submodular. So it turns out that any function can actually be expressed as a difference between two submodular functions. So f can be written as g minus h, where both g minus h are submodular. Now, the proof that we're going to do is sort of a brute force demonstration of this property. Namely, what we're going to do is we're going to define, f is some non-submodular function. We're going to add it to some all-powerful, omnipotent submodular function, which basically thwarts any meager non-submodularity by f. And then what we're going to do is say, okay, well now we've got this submodular variant of f, and then we can get f as the subtraction between the two. Right? Now that is, in some sense, a very unnatural way of doing it. But on the other hand, there are many problems for which it's very natural to express as a difference between the two submodular functions. For example, like the mutual information, which is easily expressed without any additional assumptions being required. It's easily expressed as the difference between two entropy functions. And there are many other instances as well, where, for example, you want to optimize diversity but minimize cost, and maybe you have a submodular cost model or something. But anyway, let's prove this using this all-powerful submodular function method. So let's say that f is an arbitrary function, and it's given, it's arbitrary, and you're defining alpha to be the minimum over x and y of this equality, of this quantity. Now notice that this quantity that I just highlighted in green actually is the submodular concave inequality, just all stuck on one side. It's f of x plus f of y minus the union minus the intersection. And in fact, if f is submodular, then it would have to be the case that taking the min over all x and y, we would necessarily not get anything that's negative. It would be 0 or positive. But by the assumption it's non-submodular, so that we assume that alpha has to be strictly negative. Okay. Now let's let h be an arbitrary strict submodular function. And by strict, I'll define it. Strict is defined by the value of beta. Beta is defined as the same thing. We're taking this minimum over x and y of the same submodular inequality. But by strict, we mean that beta is strictly greater than 0. Okay, so there's no point at which h evaluates x and y to be equal. There's no sort of equal point, x and y, where you're equal to the union and the intersection, which is kind of like a modular x and y. It's sort of a separable x and y. So you're never, in some sense, modular in that sense. And by beta being greater than 0, you're taking the minimum beta, and the smallest possible beta is greater than 0. You're strictly submodular. So what do we do then is we define a new function, f prime, which adds to f this sort of all-powerful submodular function. First of all, why is this component over here submodular? Because it's a submodular function scaled by a non-negative constant, right? So what we're doing, first of all, is we're normalizing it by beta, right? And beta, we said, was strictly greater than 0. So in some sense, that smallest difference is now, once we've normalized it by beta, is going to be 1. But now we're scaling it by alpha, the absolute value of alpha. And so any small, well, you tell me, so why is this f prime now submodular?
It's going to be positive. I mean, alpha is like the smallest possible, largest possible.
The largest magnitude negative deviation from submodularity. And so any sort of problems with submodularity that f happens to deal with, we know it's going to be corrected because we've got this h guy which is scaled by alpha, and we know it's at least going to be as big as alpha because we're the smallest possible thing it could be is 1 times alpha, but probably it's going to be larger because it's not going to correspond to the point where h achieved that value beta. Exactly. So therefore, what do we've got? Well, we've got then a difference of two submodular functions. Now, like I said, this is sort of a brute force way of showing it because h is any strictly submodular function. Like, for example, it could be the square root of cardinality. And you might think, what you really want, where this result may be useful, is if you're interested in, for example, expressing f and decomposing it in terms of sort of like really sort of the purely structural components. Let me try to say that again because my tongue is being twisted into knots. What I'm trying to say is, yes, you can prove this by just going ahead and using the square root of cardinality or some other kind of strictly submodular function that really has nothing to do with f. On the other hand, it becomes more interesting if it's the case that you can find a decomposition into a difference of submodular functions where each one of these submodular functions represents some truly sort of structural component in the original f. Like, I think, is a good example is in the case of mutual information. Now, in fact, we can make that a little. Yeah. Did you question? Or?
So say the previous slide, I got basically confused between why HA is compensating for the non-submodular nature of F, which we assume earlier. So what I thought is that HA is like writing over the value of F. It's like if we look at a normal graph in any case, there is a normal function, and whatever HA is adding is like is like the y-axis shift to that particular function. So if it's like a sine wave shifted up, then HA is writing over the sine wave if it's sine, right? Then in that scenario, the whole system will depend upon how F looks like. The net graph will look like F itself. Not exactly like F, but the nature of F. So it's like if in a region, if F is increasing, then any function riding on F will move in a higher direction. Right?
Yes.
So
what's your question?
So the question comes down to be if F is not submodular,
Yeah.
then whatever is riding over F will not be submodular.
No, it will be. So let's say that, for example, you've got a decreasing function, and if I add to it a large enough magnitude increasing function, it will become increasing, as long as the degree to which it's decreasing is bounded. As long as it's not decreasing, it gets a slope of negative infinity or something. So you can always make a decreasing function increasing by adding an increasing function that's increasing fast enough. Think about the derivative. Like, you take the derivative, you've got a negative derivative, which is finite, plus a positive derivative, which is finite and bigger in magnitude, makes the sum of the two increasing. And it's the same idea. Here, all we're doing is we're making sure that we're adding a function that is strong enough in its submodular inequality to dominate the violation of the submodular inequality by F. But I like the analogy to sine waves. That one was fun. Other questions?
In this whole unit graph, equals 0.
Well, remember, if alpha is equal to 0, then what happens? Then it's a submodular function already, right? So if it's alpha 0, then there's nothing we need to do. We can add 0 to it and it preserves submodularity. So, okay, here's a really important one. I think we're gonna see this again in another context in maybe a couple of weeks, but I'm putting it here because this is something that you may find surprising. So remember, a polymatroid function is a submodular function that's normalized, namely it has values 0 at the empty set, it's non-decreasing, and it's submodular. So a polymatroid function has to be non-decreasing and value of 0 at 0. Turns out that any submodular function can be expressed as a sum of a polymatroid function plus a modular function. So what that means is that all of the interesting structure, all of the interaction and the way in which items talk to each other via submodular function is via its inherent underlying polymatroid variant. And everything else is, in some sense, modular. If you were, for example, to think of this as say like a hidden Markov model for, say, sequential machine learning problem, or say a Markov random field for a computer vision one, basically it's saying that you don't, like if you have a submodular energy function or submodular smoother, it's perfectly sufficient to essentially have the submodularity be a polymatroid function for the smoother, for like the Markov chain equivalent, or whatever it is that's essentially doing the smoothing over the signal in the 1 or 2-dimensional case. And everything else is done in the unaries, or the singleton potentials, or the P of x given y, or whatever you want to call it. Those are like the unaries. So now how do we do that? I mean, how do we show that? Basically, we basically say, okay, here's some submodular G. And let's construct G hat. Maybe I can zoom in on this so we can see it a little bit. This is unfortunate, I can't zoom in today. It's strange how on Wednesday I was able to zoom, whereas today I can't zoom. So G hat of A is equal to G of A minus this thing. Now this I think we can zoom in on. So what is this thing? It's a modular function, but it consists of we haven't defined the gains yet, have we? I think we're sort of getting ahead of ourselves. I'm going to come back to this because there's a bunch of other stuff that I want to talk about. Okay. I should have put this later because we don't know what the gain is. But let me just say this. This is a very important property, which depends on having an intuition of what a submodular gain is. And what we're doing, I'll just give you a little bit of forward reference. We're subtracting up the smallest possible gain of each element, and so therefore every time we add an element to this G hat, we've got the current gain minus the smallest possible gain. That basically means each gain is non-negative. And so therefore it's a polymetric function. But let's come back to that at some other time. I'm going to skip all this other stuff. Okay, so here's the definition again. What we want to start doing is showing that these things are equivalent. So does anyone right away say, oh, these are obviously equivalent? Raise your hand if you think, yes, it's obvious. I mean, I see like within 15 seconds. So what we want to do is come up with an easy proof as to why they're the same. So it turns out that there are lots of different definitions of submodular. One of them, which let's call group diminishing returns, is the following. It basically says, it's kind of like the diminishing returns, but now it's basically saying, well, for any group. So we're saying we have A, which is a subset of B. And we have this group C. And we're saying that if we add C in the context of A, which is a subset, that's going to be bigger than adding C in the context of B, which is a superrelay. So C, even though C has cardinality greater than 1, that, potentially, becomes, this set of items becomes less valuable in the larger context. So rather than the value of our friend, this becomes the value of a group of friends. Okay. Now that turns out to be equivalent, an equivalent definition of submodularity. Now here's the notion of gain that I wanted to actually talk to you about earlier. So it's so often the case that we want to define this notion of gain. So f of A union J minus f of A. So this is the gain of J in the context of A. So we have all of these different notations that might mean the gain. So people in the past have used rho sub J of A. Other people have used rho sub A of J. Other people have used the gradient of f of A with respect to J. Other people have used f of the set J given A, and other people have used f of J given A. What we're going to use in this class is this one. And the reason why we like it is it's actually been inspired. It's inspired from information theory because that's the notation that they use in information theory. And I've seen a few other information theorists, when they talk about submodular functions, use this notation. But we like it because the name of the function is contained within the conditional form. Whereas when you have this thing, like whoops, see that's a Freudian cross out there. When you have this thing, let's say that you want to define the f of J given A and G of J given A. You have two gains you want to talk about in the same sentence. What do you do with this notation here, with the rho guys? Or what do you do with this gradient? You need to stick like a G and an F up there. And so we're just going to use this. We like this better. So with the gain notation, this is like the gain of J or the value of J or the cost of J in the context of a particular, of A or B. Submodularity corresponds to this. That's the very simple definition of submodularity. When B is a superset of A, then the gain of J in the context of A is greater than or equal to the gain of J in the context of B. Yep.
Is J a set or a member of the set?
In this particular case, J is a member of the set. Okay. However, right, so go ahead.
Also, just good. So are we only ever? You said we're going to use the last one earlier. We're going to talk about adding to
No. So we're also going to sometimes talk about adding sets. I love when that happens. It's rare. That was planned, by the way. I asked Scott to ask me that question beforehand. That was a rigged question. No, it wasn't a rigged question. You'll never know. Only we will know if it was rigged or not. You will have to ponder in mystery. So here sometimes we use gain in the context of adding a group of items. So that means that, for example, f of J given B is equal to this stuff. So now, by the way, maybe we should go back to that other example that I skipped. Because now we know what a gain is. Any questions about gain? Submodularity means that f of j given A is greater than or equal to f of j given B, right? But what if we grow the context even more? The biggest possible context would be is if we do f of j given V except for j, right? The context can't get any bigger. Right? I mean, it could get bigger, but then we just get 0, right? Because it doesn't even make sense. It's just because it's just adding j to v is still v, and so we get f of v minus f of v. So no matter what it is, it's going to be 0. So this is the smallest. This is the smallest possible gain of j that's not trivially 0. And so what we're doing here then in this guy is we're subtracting off a modular function where each item is valued by the negative of the smallest possible gain. And so any other gain, like if we were, for example, to evaluate f of, let's do this. G bar of j given A, well, that's going to be just g of j given A minus g of j given V except for j, which is necessarily going to be greater than or equal to 0 by submodularity. And so therefore what we've defined is g bar is a monotone non-decreasing function. The reason why it's monotone non-decreasing is because whenever the gains are non-negative, every time you add something, you can only increase the value. So remember, the gain is just the difference between adding a guy and not adding the guy. And since it's non-negative, that means that it has to be a monotone non-decreasing function. So therefore, we can then express any submodular function, g, as a sum of a polymatroid function and a modular function. And once we've done that, we can express any arbitrary function can be expressed as the difference between two polymatroids. So the way we do this is we say, okay, well, we first find our decomposition in terms of the difference between two submodular functions. Then each one of these submodular functions are decomposed in terms of its strictly submodular or polymatroidal part and its modular part. Then we combine it as the difference between two polymatroid functions, and we've got this modular stuff. We combine it into one modular function. We subtract the two modular functions with respect to each other. And then we take the positive part of m of g minus h and stick it in with g bar. And we take the negative part and negate it, take the positive part of the negation of m and add it into h. Right? Positive part of the negation of m, and we add it to h bar. And so now what we've got is, let's erase this so I can actually use color to designate what is what. We've got a polymatroid function there, and a polymatroid function there. So therefore, any function can be expressed as the difference between two monotone non-decreasing submodular functions. It's very interesting. Okay, so there's some applications of this, like for example, sensor placement with submodular costs. Like let's say you want to do sensor placement, but costs are often, a submodular cost is often a natural model. So maybe you want to buy in bulk, you want to experience the beauty and wonders of economies of scale, and so therefore you want to use a submodular cost rather than a modular cost. So therefore you have a value, which is maybe the mutual information, and a cost. And maybe you want to minimize, you want to maximize, that can't be right. You want to maximize cost. You want to maximize this guy, not minimize it. Right. Other forms of structure learning in graphical models use this construct of the difference between two submodular functions. So discriminatively structured graphical models for structuring graphs. Or feature selection when you have submodular costs associated with features. Like for example, once you've taken FFT, taking the third channel of an FFT renders having all these other channels come pretty much for free because the FFT is so fast. There's a submodularity associated with the FFT. Like you might if you need one channel, you might as well get all of them, and if they're useful, you can use them. So there's a strong submodularity there. It's kind of like a shared fixed cost. And also graphical model inference. Like in general, when you have a graphical model or a marker random field of some sort, and you have an energy function which is non-submodular, expressing it as a difference between two submodular functions often gives you a way of, as we don't yet know, but actually leads you to all very, very different ways of doing probabilistic inference in graphical models, besides strategies like message passing. Okay, so let's see where we are. So we're officially at 10 to the hour. So we've done the gain notation. Right. So I think the next thing we need to do is show. We want to show that this definition of submodularity is the same as this definition of submodularity, and that's the same as this definition of submodularity here. But we won't have time to do that. But I can fast forward a little bit to sort of where we're heading. Is that it turns out that we're going to get into this obviously next lecture, that if I can find the slide. There are, in fact, quite a large number of different possible definitions of submodularity, and we want to try to understand some of them. Okay, but we will derive some of these, not all of them, next time. So are there any questions? So watch out for your announcement boxes, because we do want to do a homework at some point soon. So there will be the first homework that's assigned this week sometime. And if there are no questions, then I'll see you guys all on Wednesday.